Before we go on to this video on the Lorentz transformation, I did want to add one additional thing from the previous video. When we were going over the Doppler shift for light, one thing that I forgot to mention is that that is not the same thing as the cosmological redshift. If you hear about the fact that stars from distant galaxies, as they are receding, have their light shifted to the red, and the further away they are, generally the further shifted to the red they are, that is a different phenomenon that has to do with general relativity. But now let's go ahead and pick up with the Lorentz transformation. So it's still following in the same vein of what we were doing. We can imagine that our observers S and S prime have their coordinate systems overlap at time 0, and since they're overlapping at time 0, they can both agree to start their overlapping at the same time. They can both agree to start their clocks and say that that is time 0. Right at that same moment, we emit a light pulse, and that light pulse is going to propagate out in all directions. So let's look at some time later. Sometime later, as our observer S prime is, moving with velocity v with respect to s. Sometime later, s will say this light pulse has traveled a distance x from the origin, but s prime will say that it has traveled this shorter distance x prime from the origin. Now, we know that we can't use the Galilean transformation, but the Galilean transformation was very successful when things were slow. So what Einstein and others did was they said, well, maybe we can patch up the Galilean transformation by putting in some sort of a fudge factor, let's call it k, that we multiply our Galilean transformation by. Now here, notice that I'm not using a common t anymore. I'm having to be very careful and use t and t prime. And similarly, we'll just assume change the primes, change the sign still works. And then the question is can we make this work? And the answer is sure we can. If we go and look at this light pulse situation here, we would be observing that x would have to be equal to the speed of light times t, and we'd be observing that x prime would be equal to the speed of light times t prime. Okay. So what you can do is you can stick, say, this x prime into here, you get a relationship between x and t. You can then stick that relationship for x into here, and you'll have related x and t prime exclusively. And after a lot of cranking, I'm just plain going to say that you will get that our constant turns out to be our factor gamma. So we can write, so it turns out that the correct way to transform coordinates is the Lorentz transformation. We can say that x is equal to gamma, x prime is equal to gamma x minus vt. Whoops, that should be a t right there. So x prime is equal to gamma x minus vt, and x is equal to gamma x prime plus vt prime, following our usual change the primes, change the signs thing. And I will also point out now we'll also have a relationship transforming the times. So if we go ahead and, oh doggone it, there, x, my bad. And if we go ahead and take this x prime, stick it into here, again do a lot of cranking. Eventually you'll yield the relations that t prime equals gamma times t minus vx over c squared, and t, change the primes, change the signs, is gamma t prime plus vx prime over c squared. So these transformations are what are called the Lorentz transformation. So at this point we should check and see, does this match with the correspondence principle? Okay, so remember, correspondence principle says that the new thing should look like the old thing in the limit where the old thing worked. Here, the limit of where the old thing worked was when things are moving slow compared to the speed of light. Well, if things are moving slow compared to the speed of light, the gammas go away. And so sure enough, here, with the position transformations, we're left with the Galilean transformations. It might be a little less obvious here, but the gammas would basically look like 1. But then you'd have this v over c squared. And since v is small compared to c, v over c squared is basically 0. And then you would indeed be left with t prime equals t, which was the old Galilean transformation. So yes, indeed, it does all match the correspondence principle. Now, this will have implications for our figuring out our velocity transformations. Remember before with Galilean velocity addition, all you did was you just plain added them. And we got that by taking our Galilean position transformation, differentiating with respect to time, and out popped our u minus v. Here, we have to be a lot more careful. Let's say I want an expression for u prime. U prime would be dx prime dt prime. S prime has to measure both x and t, so it'd be dx dt prime. If you look at our expression for x prime, there's a t in there. Fortunately, the chain rule comes to our rescue. We can say this is dx prime dt dt prime. Looking here, sure enough, there's just a t prime here, and so hopefully this will all work out. So let's go ahead and do the differentiations. So dx prime dt, gamma does not depend on t, so that's good. This pulls out, so we're going to be left with gamma. We will indeed have, here we will have a, ddt of x, that's good. That gives me a u. dx dt is u. Minus ddt of vt, that's just v. Good. Now for the chain rule part here, dt prime, okay, differentiating, so again I'll pick up another factor of gamma. And then let's see here, dt prime, okay, so this bit here is just going to give me 1, then plus, v is a constant, c is a constant, dx prime dt prime is u prime. Awesome. So this gives me v u prime over c squared. All right, let me clean that up just a little bit. So you can pull out a gamma squared u minus v 1 plus u prime v over c squared. Okay. Now, if we sit and think for just a second before we run off all crazy and everything, let's remember that gamma was 1 over the square root of 1 minus v squared over c squared. So that means gamma squared is 1 over 1 minus v squared over c squared. If I multiply top and bottom by c squared, because that'll probably be a little easier, this is c squared over c squared minus v squared. So let's put that in for our gamma squared. So u prime will equal c squared over c squared minus v squared. Okay. We still have a u minus v. We have a 1 plus u prime v over c squared. Now what I'm going to do is I'm going to multiply the c squared into here. So this will give me u minus v over c squared minus v squared times c squared plus u prime v. All right. Now we just have to rearrange things so that we end up purely with u prime. I'll save a few steps here because it's just algebra at this point. When you do, you will get u prime is equal to c squared times u minus v over c squared minus uv. And I can rewrite that as u prime. Again, multiply numerator and denominator by 1 over c squared. We can get the usual way of writing it, which is u minus v over 1 minus uv over c squared. So that turns out to be how our velocities add. And again, the inverse transformation is change the primes, change the signs. U equals u prime plus v over 1 plus u prime v over c squared. So let's see. First off, does this make sense? Do we get the Galilean velocity addition formulas back when things are going slow compared to the speed of light? Yeah, sure. If u and v are small compared to the speed of light, then this term is basically 0, and I get u minus v, and I get u prime plus v. Yeah, we get the Galilean transformation back. Now, let's say instead we were, throwing a photon. So remember, if someone's running along and they turn on their flashlight, everybody's supposed to agree that they get the same speed of light. Well, let's try that. Let's let u equal c and see what we get for u prime. U prime would be c minus v over 1 minus cv over c squared. Cancel, cancel. If I multiply numerator and denominator by c, I get c minus v over c minus v. Cancel, cancel. And sure enough, both observers agree that they get the same speed of light. Remembering from the Doppler shift stuff, we do see that they would disagree on what the wavelength of the light would be. So at least there's that. But they would both agree that the light was traveling at the speed of light as it was constructed to do. Now importantly, remember here, all these velocities are signed. So if things are going to the right, they're positive. If they're going to the left, they're negative. All right, let's try an example of this. So let's say that we have Elmo on his skateboard. And we have Zoe sitting over here. Whoa. Try that again. Then we have Zoe sitting over here. Zoe sees Elmo skateboarding at 0.75 c to the right. Now, Elmo's going to throw a baseball. And as Elmo sees it, that ball is going at 0.5 c to the right. And we would like to know what speed does Zoe measure for the baseball? So the first thing we have to figure out is who is S and who is S prime. So remember, whoever the narrator says is stationary or implies is stationary is S. Here, the problem is pretty clearly implying that Zoe is the is S, and so that makes Elmo S prime, which means that this is U prime. Okay, so we want to get U, and we can get that from our Lorentz transformation. It'll be U prime plus V over 1 plus U prime V over C squared. Okay, so let's put in the values. So this will be 0.75C, and that's positive because it's going to the right, plus, oh sorry, my bad. That's plus 0.5C, and that's positive because it's going to the right. Elmo is going to the right at 0.75C, so they're both positive. 1 plus 0.5C, 0.75C over C squared, cancel, 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 cancel. Okay, pop the numbers through your calculator. You'll get that the baseball is going at 0.909C to the right as Zoe sees it, which is less than 1.25C, which is what you get if you just added the two together. All right, so how can we explain that it isn't adding up to 1.25C? Well, as Zoe sees it, Elmo's clock is running slow, and Elmo's meter stick is short. Because of that, Zoe would say that Elmo would be doing too much to be adding in 0.5C. So sure enough, we would get that it'd have to be something less, and indeed it's 0.909C. Okay. So we'll finish this one up by taking a look at what's called the relativistic invariant. Which your book calls delta tau squared. So this would be C delta t squared minus delta x squared. It turns out any observer looking at any pair of events, if they calculate that number, they will get the same number. If this is positive, we'll say that the separation between events is time-like, which means that all observers will agree that the first event happened first and the second event happened second. So here's where we can still have a cause and effect relationship. If it's equal to 0, we say it's light-like. And this is just simply because the only thing that could possibly connect the two events is light traveling from one to the other. Cause and effect would still be possible. If it's less than 0, we say that the separation between events is space-like. And so this means that cause and effect are impossible. This is like the two lightning bolts striking the train car. One person could say they happened at the same time. One could say that A happened and then B. Another could say B happened then A. There's no way to have a cause and effect relationship between those two events. They're completely independent of each other. We have seen stuff like this before. If you remember from your geometry class, right? Let's say this is X and this is Y. And then we could have some other person who decides that they want to have a rotated coordinate system, like so. X prime, y prime. If you were to look at 2 points between these, this distance d here is an invariant. This d would be equal to the square root of x squared plus, well, let's actually go with d squared just to keep the harmony going here. This d squared would be equal to either x squared plus y squared, let's label these 1, 2, x2 minus x1 squared plus y2 minus y1 squared. Or we could also say that it is equal to x2 prime minus x1 prime squared plus y2 prime minus y1, plus y2 prime minus y1 prime squared. So even though they disagree on the individual values of x and y, they do agree on this d squared. That's what we mean by being an invariant. Now here, it gets a little weirder because the geometry isn't Euclidean. It's what's called a Minkowski geometry. So usually the way these things get described is we'll put x or y or z, whatever, along the horizontal axis, and we put c times t on the vertical axis. And the reason we times it by c is since everyone agrees on the same speed of light, it's a great way to convert units of time into units of distance so that we can have a consistent calculation. So here would be my event 1, there would be, say, my event 2, if I wanted these to have a time-like separation. But now the thing is that because the geometry is not Euclidean, it's going to look really weird when I draw it, but this would be my x prime, like this. This would be my ct prime, like that, and yet that is still, doggone it. And yet that is still somehow a right angle between the two. And this is just plain because it's not a Euclidean geometry, and we certainly can't draw that on a flat sheet of paper. However, we can go ahead, project down. This would be my x1. This would be going parallel this way, that x1 prime. Going parallel that way, that would be my t1 prime. And you can do similar for the event number 2. Anyway, you go ahead, you crank it into the invariant, and everyone agrees on the same value. Now, a useful interpretation of this is, let's say that we have some event happening at the origin. So we have this event happening at the origins. This is CT. This is X. Let me go ahead and draw in the 45-degree lines here. So the 45-degree lines correspond to when X is equal to CT. So any event on this cone, and this is actually a cone because we can imagine that Y and Z are coming out in the plane somehow. This cone is defined by X equals CT here, and we call this the light cone. So if we have an event sitting on the light cone, then we would say that that's a space-like separation. If we have it sitting inside the light cone, here this would be time-like. and this would be in this event's future. If the event were in this part of the cone here, it would be in that event's past. So this event can influence all the events in this event's future. All the events in this event's past can influence that event. I'm sorry, that blue one there should have said light-like, of course. And finally, if we have an event out here, let's not do it in that color. There. If we have an event out here, this would be a space-like separation. All right. Next time we will get into relativistic momentum and relativistic energy, finally getting to the E equals mc squared that you have been longing for so long. Catch you in the next one.